Welcome to MathYard Institute, where we do all things computational. All right, today we are going to look at queuing theory. All right, and we are going to partition it in series. So the first part we will introduce it, and we are going to go on as we go into complex issues. All right, what is queuing theory, right? We want to discuss what actually queuing theory is. Now, let me create a general basis of queuing theory. Why are we talking about queuing theory? So queuing theory is basically just the science of observing queues, right? Or service systems. In an example given would be you go to a bank, all right, and this is a traditional bank where you have queues where a customer has to line up into the bank, and then there are tills or tailors, they say, right? So basically they form a queue, and depending on the system of the bank, all right, there is a certain type of distribution to the tailors for attendance or to be attended to, right? Another example I would give, still in the circles of the financial systems, you go at an ATM station, right? Or an ATM machine, so to say. And at the ATM machine, because you have one machine or say three machines, you cannot all go, say you are five of you cannot all use the machines at the same time. It means then you have to queue, right? You have to line up in a certain order in order that you attend to your needs, right? Okay, so then if that is the case, why would we need queuing theory, right? So queuing theory then studies how best we can manage queues, right? How efficient can we be at managing queues, right? No one wants to stay in a queue for a long time, right? Our best is to enter the queue and exit as fast as possible, because time is a limited resource and we want to effectively use or utilize it. So if I can be at one point for the whole day, I wouldn't want it, right? All right, having introduced queuing theory in that case, the applications of queuing theory, it is used in telecommunications, right? You could be calling a certain number at the same time. So the systems at the telecommunications centers will have to put you in queues. Who called first, right? And if you called first, the incoming call or the call that comes after you cannot override you because you came first, right? So there should be a certain level of order in terms of attending to clients or machines or jobs or whatever it be. Traffic control, we know traffic lights, right? So when you go at a traffic light junction, the vehicles in this case, which are customers, they queue up, and then the traffic lights will assign based off its model, right? And so on. Now, and predicting computer performance, determining the sequence of computer operations, airport traffic, and so on. So those are just other applications. Queuing systems. So we know that queuing systems use models, right? Particular models, and the simple model or simple model of a queuing system is where you come in or you arrive this part, okay? So this part you are arriving and you queue up. If you found somebody on the queue, you be next to them, right? Then you are saved. You are, that's service time, right? Then you exit the system, all right? This is a simplified format of a system, of a model, right? But there are a lot of different models, okay, which we are going to discuss, and I will name a few, right? And I already said that you could be dealing with a customer and a saver. A saver is this particular entity. It could be if you are in a grocery store, it is a cash point or point of sale, right, where each person is attended to. If it is at a traffic center, the traffic light saver is the saver, right? And vehicles are the customers, right? And they exit. Now, and systems could have different modes of delivery or servicing, right? So you could have a structure of, first in, first out, right? First in, FIFO. I'm sure we know, if we did cost accounting, we know what FIFO is, right? First in, first out. Or first come, first serve. It will still be the same thing. So the one that comes first is the one that will be served first, or the one that comes in first is the one to exit first, right? But also you could have LIFO, right? Last come, last serve, or last in, first out, right? Which is LIFO. So the one that came last is the one that is saved first and then out, okay? But then you could also have a service in random order, where it doesn't matter who came first, as long as you are by the till, or it could be a random selection, right? It is as simple as that. It's a random selection. Okay. Having said that, we could also give a last one, actually, which is a priority order, right? Or priority service order, where, say, at a hospital, right? In as much as you could follow a queue, but the selection is priority in nature, all right? Emergency cases are always prioritized as to ordinary illnesses where you are fit. So doctors or nurses usually determine which case is more important to attend to at that particular time. So it could be a tier system arrangement where one part is priority, the other part, it could be just random selection, or it could be first in, first out, right? Usually first in, first out. Okay. Now, there are formulas attached, and these are some of the formulas. And as we go to more intense, parts, we are going to be working out the formulas even more, right? So for now, these are the formulas that we're going to use, but also depending on this problem that you are dealing with, all right? So queuing theory is in twofold, right? There's the probabilistic approach and deterministic approach, right? So deterministic approach assumes that you have been given the average waiting time, and you have also been given not average waiting time, but average arrival time, right? And you have also been given the average service time. Okay, so those are the two assumptions, and those variables are fixed. So you will be taught to say, oh, okay, given that you have 5 arrivals in an hour, or you actually save 3 machines in an hour. So you are given those two variables. While a probabilistic approach, you are now aware of your arrival time, and you are now aware of your service time, all right, or your service unit so per se. All right, and in this case, the formula is given a probability that the system is idle or empty, That is basically when you're calculating idle time. So you could be given that an employee is working for, say, 8 hours in a day. That's 9 to 5, isn't it? 8-hour job. Okay, in the 8-hour job, what is the probability that the person will be idle at that particular time, right? Or what is the idle time in that particular period of a day, all right? Then you have the average number in the queue. And in this case, let me just state that lambda, in this case, means arrival, all right, while mil is service time. Arrival time and service time. All right, so that is, so basically average arrival time in a given period of time, or average number of quantities in, all right, so let's say per time. So average quantity per time, then same as this. So service per time. So how many units do you service per given time? All right, probably standard is hours. So per hour, how many units do you service? How many arrivals come in an hour? All right. So basically, as we are looking at these formulas, we are, assuming that arrival time is represented by lambda, while service time is represented by mil. And the argument is the queue is going to be indefinite if at all. If at all you have your mu greater than your lambda. All right, so we are going to continue with the calculations in the next video. I was just creating a background to this. All right, see you in the next video. Cheers.